Let me ask you something that sounds almost too simple to be interesting. You take a glass of water, you put a spoon of salt in it, the salt disappears. You stir, it's gone. You take the same glass of water, you put a spoon of sand in it, you stir and stir and stir. The sand doesn't disappear, it sinks. It stubbornly sits at the bottom like it refuses to cooperate. Why to give? Now, most of us never really ask that question. We just say, well, salt dissolves. Sand doesn't. End of story. But that's not an answer. That's a description. It's like saying birds fly because they fly. It doesn't explain anything. And here's the funny part. Both salt and sand look similar. Tiny grains. Solid, hard, dry. You can hold them in your hand. They even make a similar crunching sound between your fingers. So why does one vanish into water and the other refuse? If you're willing to stay with me for a while, we're going to take that spoonful of salt and that spoonful of sand, and we're going to zoom in. Not with a microscope, but with imagination. Because science begins with imagination. Let's think about what it means for something to dissolve. When salt dissolves, does it truly disappear? Of course not. If you taste the water, it's salty. If you let the water evaporate, the salt comes back as crystals. So dissolving is not destruction. It's not magic. It's rearrangement. That's our first clue. Dissolving means the pieces of salt become so small, so spread out, that you can't see them anymore. They're still there, but now they're mixed evenly with the water. So what makes salt willing to break apart and mix while sand clings to itself? To answer that, we have to imagine that everything around us, this table, this glass, your hands, is made of tiny pieces, tiny beyond anything you can see. Atoms, little building blocks. Out. Salt is made of tiny repeating cubes. Each cube is built from two kinds of atoms locked together in a very particular way. If you could shrink yourself down and look at salt, you wouldn't see saltiness. You'd see a beautiful geometric arrangement, like a perfectly stacked wall of bricks. Sand, on the other hand, is mostly made of something called silicon dioxide. But don't let the name scare you. Think of it like a giant, stubborn network, not little separate cubes, but one enormous tangled structure, like a giant three-dimensional spider web that goes on and on. Now here's the interesting part. Water is not just wet stuff. Water is made of tiny V-shaped molecules. And these little V-shaped molecules are not neutral in their personality. One side of them is slightly positive. The other side is slightly negative. So water is like billions of tiny magnets swimming around. Now imagine you drop salt into this ocean of tiny magnets. The salt crystal is made of positive and negative pieces arranged neatly together, and the water molecules are attracted to those pieces. The negative side of water hugs the positive part of salt. The positive side of water hugs the negative part of salt. It's like a crowd of tiny dancers surrounding each salt particle, pulling it gently away from its neighbors. One by one, the salt pieces get surrounded, pulled apart, and carried into the water. It's not that salt wants to dissolve. It's that water loves to grab onto its pieces. Dissolving is a love story. Now what about sand? Sand is not built from little positive and negative blocks that can easily be pulled apart. It's more like a giant continuous network. Imagine trying to dissolve a brick wall by throwing magnets at it. The magnets might stick to the surface, but they can't pull the wall apart into individual bricks if those bricks are permanently glued together. Water can wet sand, it can flow around it, but it cannot easily break its internal bonds. The structure is too strong, too interconnected. So sand remains sand. Salt falls apart into tiny invisible pieces, because water can sneak in between its building blocks and separate them. Sand resists because its structure is more like one enormous molecule stretching through the grain. Now here's something even stranger. If you grind sand into finer and finer powder, does it dissolve? No. If you heat sand until it melts, what do you get? Glass. Glass is basically sand that has been melted and cooled into a different shape. And even glass doesn't dissolve in water. So the difference between dissolving and not dissolving is not about size. It's not about how small the grains are. It's about how the atoms are arranged and how strongly they hold on to each other. And that's the deeper lesson. On the surface, salt and sand look similar. But at the invisible level, they are completely different worlds. Isn't that astonishing diet too? two white powders, two similar textures, completely different microscopic architectures, completely different microscopic architectures, completely different behavior in water. And this is how nature works. What you see is often misleading. The real explanation hides at a deeper level. Let's go even further. Why does water bother to pull salt apart? Why doesn't it just ignore it? But because nature tends to move toward arrangements that spread things out. When salt dissolves, its pieces are more spread out than when they are tightly packed in a crystal. There's more disorder, more mixing. And nature, strangely enough, prefers that. If you spill perfume in a room, the smell spreads. It doesn't gather itself back into the bottle. If you drop ink into water, it spreads into cloudy swirls until it's evenly mixed. Things move from clumped to spread out. Salt dissolving is another example of that. General tendency. Sand, however, would require breaking extremely strong bonds to spread out its pieces. The cost is too high, so it stays together. Now pause for a moment and think about this. Every time you cook pasta and add salt to boiling water, you are watching billions upon billions of tiny electric interactions happening instantly. Invisible dramas playing out in silence. It looks boring, but it's not boring at all. It's the universe rearranging itself in the most efficient way possible. And here's something that always fascinated me. If you take salt water and evaporate the water slowly, the salt comes back in perfect cubes again, as if it remembers its original shape. But it doesn't remember, there's no memory. There's just physics. When the water leaves, the salt pieces attract each other again and settle into the most stable arrangement, which happens to be a cube. Order disappears and reappears depending on conditions. So dissolving is not a permanent transformation. It's conditional. Change the environment and the structure changes. Isn't that a bit like life? Under one set of conditions, we behave one way. Change the environment, and we rearrange ourselves. But let's not drift too far into poetry without finishing the science. Some people think dissolving is about melting. It's not. Melting happens when a solid becomes liquid because heat shakes its particles loose. Dissolving happens when a liquid pulls apart a solid and surrounds its pieces. Different processes, same result. Something disappears from sight. But disappearance is often just a trick of scale. If you had eyes small enough, you would see salt ions swimming freely between water molecules. You would see constant motion, jostling, colliding, vibrating. Nothing is still. Even the glass of water sitting quietly on the table is a storm at the microscopic level. And sand sit in at the bottom of it. Its atoms are vibrating too, but they are locked into a rigid network, like dancers who are tied together at the waist. They can wiggle, but they can't separate. Water molecules bump into them, but the structure holds. Now here's a question. Could we dissolve sand? Under normal conditions, no. But in very strong chemicals or at extremely high temperatures, yes, you can break it down. But that's not water anymore. That's a different environment with different rules. So dissolving depends on the relationship between two substances. It's not that salt is dissolvable in general. Salt dissolves in water because of a particular compatibility. In another liquid, maybe not so easily. Compatibility. That's the secret word. Water and salt are compatible at the atomic level. Water and sand are not. And that idea stretches far beyond chemistry. Some ideas dissolve in certain minds, and not in others. Some people blend beautifully in certain environments and not at all in others. Structure matters. Compatibility matters. But back to our glass of water, imagine shrinking yourself down to the size of a water molecule. You're swimming around, you encounter a giant salt crystal wall. You're attracted to parts of it. You cling to a corner. Another water molecule joins you. Then another. Slowly you pry a piece loose. It's not dramatic. It's not explosive. It's subtle, collective, patient. Nature often works that way. Not with one big push, but with billions of tiny nudges. And that's the real proof behind salt dissolves, but sand doesn't. Not magic. Not mystery. Just structure and attraction. Architecture and compatibility. When you understand that, something shifts in your mind. You begin to see that the properties of the world are not random. They emerge from invisible patterns. Salt tastes salty because of its atoms. Sand feels gritty because of its atoms, of its network. Water flows because of its molecular shape. The everyday world is a shadow of deeper arrangement. And the most beautiful part is this: you don't need complicated equations to appreciate it. You just need curiosity. The next time you see sugar dissolve in tea, or watch waves wash over sand at the beach, remember that you are witnessing a conversation between structures, a negotiation of forces. Some partnerships succeed, others fail. Salt and water succeed. Sand and water do not rand. And yet both obey the same underlying laws. There is a kind of humility in that realization. The universe is not built around our categories: solid, liquid, dissolve. These are our words. Underneath, there are only atoms following simple rules. Rules so simple that they fit everywhere. In your kitchen, in the ocean, in distant planets. Think about the ocean for a moment. It's salty because rocks on land slowly dissolve over millions of years, releasing ions that rivers carry to the sea. Salt that once sat in stone now swims freely in water. The entire ocean is a giant example of dissolving. But the sandy beaches remain sandy. The grains roll under your feet. They don't vanish into the waves. Same water, different structure. If that doesn't make you pause and feel wonder, I don't know what will. Because in that simple contrast, salt disappearing, sand remaining, lies a profound lesson. Reality is layered. What we see depends on scale. Behavior depends on structure. And understanding begins when we refuse to accept that's just how it is as an answer. So next time you hold a pinch of salt in one hand and a pinch of sand in the other, don't just see two powders. See two architectures. See two different ways atoms can arrange themselves. See billions of tiny electric attractions determining the fate of a spoonful in water. And ask yourself, what else in this world looks similar on the surface, but is completely different underneath? How many mysteries hide in plain sight? Science doesn't kill wonder, it deepens it. When you know why salt dissolves and sand doesn't, the world doesn't become dull. It becomes alive with invisible activity. The glass of water on your table becomes a microscopic universe. And you realize something beautiful. The ordinary is not ordinary at all. It is extraordinary. Quietly, patiently, endlessly extraordinary. And that, my friends, is the real proof.